scale is the new scale used over the Richter scale in most cases, it kind of demonstrates a larger difference in actual magnitudes. So you can see that a higher number on a moment magnitude scale is actually a much larger difference in the energy released versus in the Richter scale. The same range difference would be a little bit less change in magnitude. And basically, the thought was that the earthquake happened due to a weakened plate boundary based on the composition, structure, and different sediments that are located in the plate where it happened. So the proposal of this research was that the properties of faults can lead to slips in the faults. So there's a trench located off the coast of Japan. It's about 200 miles, or 200 kilometers off the coast. And basically they wanted to look at the frictional properties, the composition, and the structure of this subducting plate or this trench. So basically with the frictional properties, they can test actually if they gather sediments or different parts of core samples, they can test them in a lab setting and actually put them under pressure and see if they'll slip, if they'll fracture, different tests like that to see the frictional properties. Composition, obviously with a core sample, they can look at the different sediments, they can look at the different age ranges and see how they're interacting within the core. And then the structure, just the orientation within a core sample, say if you've got parallel strata versus slanted strata, you can tell the difference in if there has been any tectonic activity, any plate slips, and different things like that. So in this study, they had two different groups come out and help out. So they had the JFAST project, which is the Japan Trench Fast Drilling Project. That's one of the boats that they had. And they also had the IODP. IODP is the Integrated Ocean Drilling Program. So these two kind of teamed up together, went out, did studies, they ran seismic surveys in the area, they took core samples, and did all their data. It's kind of a joint effort. They ran two expeditions. There was Expedition 343 and 343T during the time period of the study. So the drill site, that's the most important part of the study, where they gathered their cores. And they labeled it drill site C0019, just a scientific label, obviously. It was about 200 miles off the shore of Sendai City in Japan, and it was actually located over a horst. So I'll show you the next picture. So a horst is actually an uplifted piece of tectonic material versus a graben is a kind of pressed piece. So along a plate, it'll go horst, graben, so you've got uplifting and depression. So basically, in this diagram, the top one on the left, part A, this star here is the epicenter of the Tohoku Oki earthquake. What you've got here, this dashed line along the top is actually a tsunami, and its range in 1896. So that was a previous tsunami that they kind of compared the data to. And then here is actually site C0019. The dot is where the site is, where the actual core was taken, and that line that you can see going across there, that's this transect right here, this basically cross section. So if you look at figure B, this is a blown up section of that line, as I said. So this is from the side. What they did is they actually ran seismic surveys along to send out different types of radiation and look for bounce back. We can basically map the ocean floor within the seafloor versus just on the top. So you can see here you've got the depth in meters below sea level. That's what the MBSL stands for. Also, you might see meters below sea floor, so MBSF. So here, this red line represents where the core was taken. It came down through, it's about 6,500 meters below sea level. And then beyond that, they went about another 1,000 meters into the ground. So here you've got the forest, as I said. You can see here, this is actually where the trench is. The Pacific plate is coming in and subducting underneath what they call the prism, which is actually what Japan sits on top. So it's more of a continental plate versus an oceanic plate, as the Pacific plate is. So that's the trench, and this is what's going on as it subducts. Up in figure C, you've got the core sample again, and this is about the bottom of it. The goal of the core sample was to go past the actual plate boundary, so they wanted to be able to get the crustal plate, basically part of the prism in the core, as well as where it overlaps and goes into the specific plate that's ducting below. So they wanted to have the above, where the frictional properties are actually happening, where the plate is sliding, as well as below, so they can see the different makeup of the below. Here, as I said, they ran seismic surveys that send out basically radio waves, different types of radiation, and they look for bounce back from different materials, different sediments within the actual, within the plates. So up here, you can see that this is all pretty much finer sediment, smaller sediment, but these dark lines are where there's a more pronounced change in the type of sediment. Sometimes it could be thicker rock, more dense rock, different areas like that. So you can see this is all the prism above. This is the Pacific plate below. It matches up to right here perfectly, and you can actually see this force and gravity, the shifting, the uplifting, and the downwelling. That is exhibited here where there isn't that parallel strata as I was talking about. So when it's shifted, you can tell that it has been sliding past or been shifted in some way due to conductivity. So the techniques that they used for this study were they used 3 holes. They were all drilled. They were all drilled in the same area. They're very close proximity. They didn't say how close, but each hole was used for a different thing. So they were all drilled to about 844 meters below the sea floor. So they wanted to reach the basalt, as I said, pass through the actual zone where the 2 plates are meeting. The logging while drilling technique is not logging as in like tree logging, which is kind of what confused me at first. It's logging like data. So basically there's a sensor in the hole that they're actually drilling down the core maker, and it takes data while it's going. So this one, logging while drilling, it recorded depth, and what it does is it sends out gamma rays, and it has resistivity sensors that are able to pick up the different depths to be able to measure that for the core sample. So hole number 2 was actually where they took the core. So it was taken from specific depths. I'll show you later on in the diagram of the actual core itself. But they didn't use the whole 1,000 meters or anything like that. They kind of threw some out. Some was unusable, so they only had certain amounts that were actually usable data. And then the 3rd hole was able to temperature sense, and they used that to correlate depth for the different grid codes. So what they found mostly in measurement is that the top of the geologic plate, so the Pacific plate, is at 820 meters below the seafloor. And then they could tell based on other surveys that were done previously that this was in the same vicinity as those reflectors in the first picture. So where that change in the reflectivity of those seismic waves in that seismic survey. So the plate boundary zone, they described it as consisting of a scaly fabric. So that's kind of how they use what they use to describe that sediment there. It's about 1 meter thick, as you'll see in the slide. And they found it at about 821 to 822 meters below the seafloor. So it's a very small layer, a very small percentage of the core that was actually scaly fabric. What they found in the scaly fabric was a different log signature, lithology, different chemicals. There were fluxes in potassium, calcium in this part of the sediment that distinguished it from different other layers. The scaly clay was found to be from the Paleogene time era, and it was actually moved there due to a slip fault. So that's not actually where it would occur. What would happen is while it's faulting, it ends up getting deposited there. And then around the scaly clay, there's about a 10 meter thick zone of just deformation due to the fault slip. So some different observations that they found of the actual scaly clay was that it's very lush and it's very striated. So the striations show that it's been shifting, rubbing back and forth against each other for a long period of time. It's usually a red-brown or dark brown, black this is the second diagram in the paper. What you can see, you've got depth on the left axis, and you've got, this is the core sample. So you've got, these are all different data based on this core sample here. For sections, the black ones are ones that were usable sections, and the white is areas that they either just didn't want to use, didn't need to use, or it was unusable due to some other thing that happened. So what we're going to look at mostly is the scaly layer area, which is about 822 meters below seafloor. And then above it is that folded prism that I told you about, the Japan basically plate, and then below that is the Pacific plate. So looking along from 690 to 820 meters below seafloor, they found Pleistocene radiolarians. So that's how they were gauging it based on the different fossils that they were able to find in it. From 800 or at about 820 meters below seafloor, they found that the bedding actually dips. So these are the dips in bedding. So when the bedding dips, that's where they can attribute it to sloping of the gradient. And then it also shows very high gamma ray signatures, and so that's right here. So at about 820, the gamma signatures increase, and then falls again at 836-ish meters below seafloor. And in that section right here, about there to there, they found that there are late Miocene mudstones and Cretaceous pelagic clay. And then after this point, it converted to chert from the Cretaceous era. So looking at this core sample, this is kind of blown up of this small section of about the 1 meter. So this is about 1 meter's worth. And in it, you can see the different colors, different coloring of the clay, or of the scaly fabric. And you can also see these white dashed lines are kind of an outline of the different scaly clays. So you can see that there are some that are horizontal that haven't been shifted necessarily, and there are some that are on the angle, which shows the decline. So conclusion-wise, basically they found that there are a lot of non-parallel slips. So when they're not parallel, that does show that there has been deformation, and that when they find them in this area that's a little bit weaker, the scaly fabric, it's basically showing that since it is weaker, it's where the slip is happening. They're able to pass near each other faster, or basically have a more profound effect on the trench. Compared to other drilling sites, this is a thinner fault zone, so like I said, it's about 1 meter thick. And then there's a lot more scaly fabric compared to other drilling sites as well. So that leads them to the conclusion that with the scaly fabric, that actually does help the seismic activity here because it's not as prominent in other areas where it's less likely to happen. And then the scaly layer is again weaker than the surrounding sediments, and the seismic activity is really exhibited in that particular. So just some closing thoughts. Incoming plates do have an influence on the location and structure of faults. As I said, the scaly clay wasn't there originally, and the plate tectonic movement is actually what brought it into the area and is now where it resides on the fault. The JFAST drill site sediments are actually similar to those that are along the entire trench, along a lot of the North Pacific plate. And basically that says that throughout the whole region, you can find a lot of the same similarities. Sometimes you can have the same slips, faults, things like that in the area. And then there are also similar properties of the Japan Trench that represent a larger picture of the plate. So you can kind of follow and assume that the scaly fabric goes along about the same depth, about the same amount along that trench. So I'd like to thank Chester et al. From 2013